We're going to begin Physics 213 and we'll start with Chapter 18. Physics 213 deals with thermodynamics and fluids. And Chapter 18 is about thermodynamics, the zeroth law, and the first law of thermodynamics. So what exactly is thermodynamics? Thermodynamics is the study of thermal energy of system. And so it basically deal with the temperature. These are the parameters that you'll be dealing with, like temperature, pressure, density, and specific heat and heat engines. These are the topics of thermodynamics. And so what is Zeroth law of thermodynamics? There are three laws. The first is the Zeroth law, and then after then that's the first law and the second law. Okay, the reason why the zero we don't begin with the first law but with the zeroth law is because people discover the first law before the zeroth law, but the zeroth law is so fundamental that it has to be a law. So we put it in front of the first law, so it becomes the zeroth law of thermodynamics. So what is Zeroth law of thermodynamics? It states that when you have an object A, let's say it has a temperature that's called T sub A, and then you have an object T, let's say it has a temperature that is called T sub T. If object A and object B are in thermal equilibrium, if they are in thermal equilibrium, which means that the temperatures are equal to each other. So T sub A is equal to T sub T. Now, if object T and object B are also in thermal equilibrium, which means that the temperature of object T is equal to the temperature of object B, then what we can deduce, and this is what comes the Zeroth law of thermodynamics, what we can deduce is that object A and object B, they have to be in thermal equilibrium and the temperature has to be equal to each other. So this is the Zeroth law of thermodynamics. If A and T are in thermal equilibrium, T and B are in thermal equilibrium, then A and B must be in thermal equilibrium, and the quantity that defines them to be in thermal equilibrium will be the temperature. So the temperature has to be the same. Okay. Now, speaking of temperature, how do we find temperature? Okay. What we know is that by ideal gas law, which we're going to discuss in the next chapter, from ideal gas law, we found that temperature is proportional to pressure when the gas density is extremely low. So the temperature at any given pressure can be found, and let's say so your T, this is the unknown temperature, and the reference point is 273.16 Kelvin, which we're going to discuss it immediately after this, and times the limit P over P3, and when the gas density is low, which means that it's approaching the zero. And so this equation tells you that temperature at any pressure is equal to a constant 273.16 times the ratio of the pressure of the object at temperature T divided by the pressure at P sub 3. So what is P sub 3? This is the pressure. This is the pressure of water at the triple point temperature. Okay, so you can see that temperature basically is proportional to pressure, and the temperature at any given pressure can be calculated using can be found using this equation. So what is triple point of water? What we found is that H2O, which is water, can coexist in three phases. What are the three phases? The ice, which is the solid state phase, water, which is the fluid, and the other one is water vapor, which is the gaseous state. So the water or the H2O can coexist in three different phases when the temperature is at a certain temperature, and that temperature is at 273.16 Kelvin. and this temperature is what we call the triple point temperature. So in other words, when the temperature of the water is at 273.16 Kelvin, then the water can exist in these three different states. They can coexist. And the pressure at this temperature is what we call the P sub 3. So in other words, once you know that the pressure at the triple point temperature, and when water reaching a different pressure, you can calculate what will be the temperature using this equation. And the SI unit for temperature is Kelvin. And this Kelvin is the one that we use in scientific world. And however, you'll find that we don't usually use Kelvin when we speak. When people ask you what is the temperature of today, basically people would, depending on where you live, if you living in the United States, of course the temperature will be in Fahrenheit. If you live in the rest of the world, then most likely people will tell you the temperature in Celsius, which is we use capital C to indicate that, and Fahrenheit, that's an F. So what is the conversion? Conversion for temperatures in different units. If you're given the temperature in Kelvin, then the temperature in Celsius will be just equal to the temperature in Kelvin minus 273.15 degree. Okay, so this is the relationship between temperature in Kelvin and the temperature in Celsius. It differs just by a constant 273.15 degrees. What about when you have a temperature that's in Celsius and you want to find temperature in Fahrenheit? Then this is the question to use. Temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32 degrees. So here's a simple exercise that you can do. Let's say when you have a temperature at 0 degrees, what will be the temperature in Fahrenheit? Then, because you know the temperature in Celsius, you just put 0 here, and then so your temperature in Fahrenheit will be just 32 degrees Fahrenheit. What about when you have a temperature that's at 100? When the temperature is at 100 degrees Celsius, you plug into here and then plus 32, then you will get 212 Fahrenheit. So that's basically these are the equations that you'll find that very comes in handy when you want to do the conversion. And the next concept that we want to discuss is about thermal expansion and contraction. So let's say when you have an object, and let's say initially is at a temperature T, but now you're increasing the temperature. Would the size of the object change due to the temperature change? And the answer is yes. When the temperature increases or decreases, the size of the object is going to expand or contract. Okay, so how do we find the change in length or the change in length or the change in volume of an object when there's a change in temperature? And so let's look at the one-dimensional case where you have a linear expansion. So this equation tells you that the change in length, delta L, that's equal to L, the original length of the object, times alpha, which is a constant, and then times delta T, which is the change in temperature or the temperature difference. Okay, so what is alpha? Alpha is the coefficient of linear expansion. So let's look at this picture. So I say you have an object with the original length at L, and then the temperature is initially at T sub I, and when you increase the temperature, so the final temperature is greater than the initial temperature, then you find that your delta T is greater than 0. When delta T is greater than 0, when you plug into this equation, you'll find that your delta L is also greater than 0 because L times alpha times delta T is a positive quantity. Now, if you have the initial if delta T is less than 0, when you plug into this equation, then you'll find that it is subject to a contraction. So in other words, the length now is actually shorter than the original. Okay, so this is the original, and then so you can see that this is your delta L, and you'll find out your delta L is less than 0. Okay, this is when delta T is less than 0. Okay, so this is when you have an object that experience a temperature change, then the length would change as well. And what about when we are dealing with object? Usually is a three-dimensional world, so you have to think about in each dimension, the size of the object will change according to the change of the temperature. So the volume expansion can be calculated using this equation. And the volume expansion is equal to the original volume of the object times a constant, which is the coefficient of volume expansion, beta, and then times delta T. So in other words, when there's a change in temperature, it's going to cause a change in volume as well, and the change in volume can be calculated using this. Most of the time, you'll find that the coefficient of volume expansion is 3 times the coefficient of linear expansion. So you don't really need to know beta as long as you know alpha, and then multiply by 3. That gives you beta. Okay, so you want to see table 18-2 for the coefficients for different objects. Let's say you have wood, or if you have plastic, if you have a glass, if you have like iron, a piece of iron, what is the coefficient of linear expansion? So all this information is listed in table 18-2. Okay, so you can see that when there's a change in temperature, the size of the object is going to change. So that's why when we design something, we most of the time you need to take into account the thermal expansion and contraction. So you want to make room for the changes due to the temperature variations. Okay, all right. Now the next one is the next concept that we want to talk about is energy as heat. Okay, so what is energy as heat? So let's look at this. When you have two objects in different temperatures, which means that they are not in thermal equilibrium, because the prerequisite for them to be in thermal equilibrium will be that their temperatures are equal. So when you have two objects in different temperatures, they are not in thermal equilibrium. Then there's going to be an energy transfer as heat. Okay, so heat is one kind of energy, and when there's a temperature change, then the heat is going to flow from the hotter object to the colder object. And when will the heat transfer be stopped? The heat will be transferred, when these two objects reach a thermal equilibrium. So in other words, the heat will continue to flow until both objects have the same temperature. Okay, and so capital Q is what we call heat. It is positive. We consider that as positive when energy is transferred to the system. So in other words, when the system obtains this energy, then Q is positive, and Q is considered negative when the energy is transferred from the system. So in other words, when you transfer into the system, it is considered gaining. When the energy is transferred from the system, so in other words, the system is releasing heat, then it is considered as negative. So let's look at three cases. So we have what we define as environment, and this is the system. So you have a system that is, in the environment. So this is like you in a classroom. You is considered as a system, and the classroom is considered as environment. So let's say the system has its own temperature. The temperature we call that T sub S, and the environment has its own temperature that's called T sub E. And that's in case one, when the temperature of the system is greater than the temperature of environment. So in other words, when you're hotter than the classroom, then what's going to happen is that because your temperature is higher, so you're going to release heat, you're going to release the energy. So the energy flow is from you to the classroom, or from the system to the environment. So that because you are losing energy, so your Q here is considered as negative because you're losing energy. So let's say you have case 2 when the system and the environment have the same temperature. If the temperature of the system and the temperature of the environment are the same, then there's no heat transfer. So in other words, there's no Q. Q is equal to 0 because both the system and the environment have reached an equilibrium, a thermal equilibrium. Now let's look at case 3. In case 3, we found that the temperature of the system is smaller than the temperature of the environment. So in other words, a classroom is hotter than your temperature. So it's hotter than you. So in that case, what's going to happen inside the environment is going to transfer energy from the environment to the system. So the directions of the heat flow is from the environment to the system. And in this case, because the system obtained energy, and we consider that as positive, so your Q is positive. It's greater than 0. Okay. So, so this is basically tells you that when you have system and environment, they are not in thermal equilibrium, then there's a heat transfer. And the directions of heat transfer really depends on which one has a higher temperature. If the system has a higher temperature, then heat is going to flow out of the system. If the system has a lower temperature, then heat is going to transfer to the system. Okay, and because heat is one kind of energy, so we know that the SI unit is in joules. However, in the past, people don't use joules that much. They have another unit, which is calorie, and because it has been used so popularly, it has been used so commonly, so that's why we keep both systems. We keep both units, calories and joules. And so how is it? So 1 calorie is equal to 4.186 joules. So let's say you open up, you have a snap bar which tells you that's 140 calories. Then how many joules is in that bar? Then just use 140 calories times 4.186. That will give you the amount of energy in joules. Okay. So because we know that when there's a temperature difference, the heat flow is due to the temperature difference, and the heat flow will stop when the temperature difference is 0. So based on that knowledge, we know that the heat flow is proportional to the temperature difference. And so what we can write is that heat is equal to a constant times delta T because it's proportional to the temperature difference. Delta T, of course, is the final temperature minus initial temperature, and that's your temperature change. So what is this C? This C is what we call heat capacity, and heat capacity is the proportionality constant between Q and the temperature change. Okay, and what we found is that heat capacity is not really a very is not a really useful quantity. What we want to know is the specific heat. And what is the definition of specific heat? Specific heat is defined as heat capacity per unit mass. So in other words, the heat capacity not only depends on what kind of material. It doesn't matter how much mass is contained because it's heat capacity per unit mass. Okay, so this equation becomes Q is equal to mc delta T. M here is the mass of the object. Let's say the more massive of the object, then the more heat is required to transfer to or from the system. And C, of course, is called the specific heat, and delta T is the temperature change. So we have mc and then times the temperature change. So what is the specific heat? So you might wonder what is the difference between heat capacity and specific heat? Specific heat we use a lowercase. Heat capacity we use a capital C. We use capital letter, and it is a proportionality constant, and it depends on the size of the object. See here, the lowercase c specific heat does not depend on It does not depend on the size of the object. It only depends on what kind of object we're dealing with. Okay, so see here, the units for specific heat is 1 calorie per gram times degree Celsius. And if you want to convert everything into SI unit, then that's equal to 4,190 joules per kilograms per Kelvin. Okay, you'll find that this is one we use a lot, especially in scientific world. We use this, we seldom use this, but then in everyday life, you probably will use this a lot more than using this one. Okay, and so table 18-3 lists lists the value of specific heat for different objects, and the other specific heat that we use a lot is what we call the molar specific heat, and that we use it for gases, and it is defined as specific heat per mole. Okay, and which we're going to revisit more specific heat in chapter 19. So the next one is called the heat of transformation. Now, previously we discussed that when there's a temperature change, then there's a heat flow. Now, this time, this slide will focus on when there's a heat flow, it does not necessarily use it to raise the temperature, to change the temperature. So there are cases when energy is transferred, but the temperature does not change. So where does that energy go when there's an energy transfer, but it does not go into raising the temperature? The energy is used for phase transition, and so in other words, the energy does not go into raising the temperature, but the energy is used to change the phase of the object. And the amount of energy and this kind of heat we call a heat of transformation. And the amount of energy is equal to L times N. So what is L? L is what we call the heat of transformation. What is M? M is the mass of the object. So in other words, when this amount of heat Q go into when there's an amount of heat going to the object, then it does not raise the temperature, but instead it's changing its phase. So it can change from gas to liquid, or from liquid to gas. We can go from solid to liquid, or liquid to solid. So this is what we call the phase transition. And so Q is equal to Lm. So L is heat of transformation, and there are two different L. One is heat of vaporization, L sub V, and one is called the heat of fusion, L sub F. Okay, so two different kinds of heat of transformation. When the heat goes to change the phase from gas to liquid, or liquid to gas, then this is called the heat of vaporization. When the heat goes to change from solid to liquid, or liquid to solid, then this is called the heat of fusion. Okay, so for water, because we're going to do simple problems using water, applying to water. So these are the numbers. These are the heat of transformation for water. So heat of vaporization has this value, 439 Kelvin per gram, or 2,256 kilojoules per kilogram. Here, make sure that you remember when you do problems, this kilo, you have to multiply by 1,000, become joules, because kilojoule is not a standard unit. Joules is the standard unit. So it's 2,256 kilojoules per kilogram. What about heat of fusion? Heat of fusion for water is 79.5 calories per gram, or is equal to 333 kilojoules per kilogram. Again, it's kilojoules, so we have to convert it to joules. So what about the Hiller transformation and Hiller vaporization for other objects? In that case, you want to look, you want to see table 18-4 for the L values for different objects. Okay, so the previous slide deal with when there's a heat, when there's a temperature, there's a temperature change, there's a heat flow. And this slide deals with when there's a phase change, there's a heat flow. So combining these two effects together, this is the equation. This is the optimal equation that you want to use. So in other words, heat transfer, the net heat transfer has two terms. One deals with the change in temperature, one deals with the phase transition. So it is mc delta T plus or minus Lm. So m is of course is the mass, c is the specific heat delta T. So delta T here, we didn't put a plus or minus in front of the first term. That's because delta T itself will tell you whether the temperature is increasing or decreasing. So delta T here can be positive or negative. And then you have the Ln, which is the Hiller transformation. The Hiller transformation can be positive or can be negative, depending on what phase transition is takes place. Okay, so L here is Hiller vaporization, and of course is the mass. So just to remind you that everything has to be in SI unit. So in other words, the mass has to be in kilograms. Specifically, has to be in the unit, the SI unit. Delta T has to be in Kelvin, and L of course has to be in this unit. Has to be in joules per kilograms, and again mass has to be in kilogram. Okay, so as you can see, we have plus or minus. So you have to decide when do you use plus, when do you use minus. We use plus when you have a phase transition that's going in this direction from solid to liquid, from liquid to gas. If the direction is going in from solid to all the way to gas, then you want to use plus because the object needs to absorb heat in order for the phase transition to happen. If, however, if you have a phase transition that goes from gas to liquid to solid, then in that case you use a minus because the object has to release heat in order for it to go through the phase transition from gas to liquid to solid. Okay, so that's basically this. These are the basic principle that you want to go by when do you, and also determine when do we have to use plus, when do we have to use minus. So let's say you have ice cube. If you have ice cube that you want to go from ice cube to water, then the phase transition the kind of phase transition is what we call a Hiller fusion. So for Hiller fusion, you in this equation, then you will use L sub F, and then you have the mass of the ice cube, and then because you go from ice cube to water, so you want to use a plus because energy has to be added to the system in order for the ice cube to melt and then become water. And of course, if you want to make the water into a water vapor, then that involves the Hiller transformation, and that kind of Hiller transformation is the Hiller vaporization. So in this case, Hiller oh, I think I have a spelling wrong. Vaporization. Yeah. Okay, Hiller vaporization. And so for the Hiller vaporization, then from water to water vapor, then the water needs to require heat in order for it to change to water vapor. And that's something is common sense because if you boil water, and then water itself initially is a liquid form. When you boil water, you start seeing the bubble and you see the other gases, the water vapor that's coming out of the water, and that's why. And then you are actually, put the energy. You put the energy into the water, and then so that water has enough energy to turn into water vapor. Okay, so this is water vapor. This is vapor. Anyway, so I think this is wrong spelled. Okay. so this is the equation. This is the equation that involves two terms. One is one deals with the change in temperature, one deals with the phase transition, and this is the principles to go by. When do you use plus, when do you use minus? Okay. So the previous slide deal with when you have water, when you have, let's say, metal, and when you have, like, say, glass, wood, and then this is, you use this equation to calculate the amount of heat transferred. Now let's look at the situation when we deal with gas. So let's say this is the piston. Okay, so you have a piston and you have a lead. So this is the lead. Okay, and then you have all the gas molecules that's under the lid. Okay, so let's say, um, so let's say you want to, if you turn up the temperature, so the gas become very agitated. It's going to push up, and then it's going to expand. The gas is going to expand because the raise of the temperature. So the lid is going to be pushed upwards. So what is the amount of work that's done by the gas when that happens? When all the gas molecules trying to expand to it, to flow, and push the lid, upward. So the amount of work done by the gas during the displacement is, we know that the definition of work is differential work is dW, which is F dot ds. F, of course, is the force, and ds is the differential displacement. So what is your F here? F is the force. So what kind of forces does the gas exerted on the lid? And that force is what we call the pressure force. And how do we calculate the pressure force? This basically will be dealt with in chapter 14. So which is we're going to discuss it, after we're done with the thermodynamics. So just take my word that this F is the pressure force, which is the pressure of the gas exerted on the lid, and A is the cross-sectional area of the lid. Then ds is the displacement. So dW is equal to the pressure force P times A, and then ds. So what is A times ds? A is the cross-sectional area, and ds is the displacement, and that will give you the differential volume dV. Okay, so this equation becomes pressure times dV. And so when you integrate on both sides, the amount of work that is done by the gas is equal to P times PdV, and you integrate that from the initial volume to the final volume, and that will give you the amount of work. So you can see that the amount of work really, depends on the volume. If there's the change in volume, then there's a change in work, or there's a heat flow. Okay, so so this is the equation that we're going to revisit quite a bit when we deal with gas. Okay, and the next thing we want to talk about is what we call the PV diagram. What is a PV diagram? A PV diagram is, you have a P pressure on the vertical that's on the vertical axis, and you have volume that's on the horizontal axis. So any point on this PV diagram indicate the state of the gas. So in other words, at this point I, you know the pressure, you know the volume, and by ideal gas law, you pretty much know the temperature, and you know the density of the gas. So the PV diagram is very important with in thermodynamics, because any points on the PV diagram gives you the state of the gas. Any point on the PV diagram, you know the pressure, you know the volume, you know the temperature. Okay, and the concept about this is that, let's say you have a piston, and we draw the state of the gas on the PV diagram, and you have an initial point I, and then the volume. Let's say the gas is doing work, and it's pushing the lid upwards. So you have a volume expansion. the final volume is greater than the initial volume. And so on the PV diagram, you could draw like this. So this is the process from point I to point F. That's a process. You can see that the initial volume is greater than the final volume. So using this equation, we know that the amount of work done by the gas has to be greater than 0 because it's pressure times you integrate dV. And whenever you're dealing with the integration, that's PdV, basically it will be just the volume or the area under the curve. This is just based on the calculus, and this is actually the basic principle of calculus. When you have PdV, when you have two quantity and you integrate, you integrate the quantity and then draw them on this x and y axis. Then the amount of when you do the integration, it is equivalent to finding the area under the curve. So this is the PV diagram, and from this diagram we know that the amount of work done by the gas is positive. So that's how about now if we reverse the process? Let's say we still have the initial point I, we still have the initial point F, but then it is not going from I to F, it's actually now going from F to I. So in other words, you put the lid is pushing down, so that the volume becomes smaller. The volume becomes smaller, and then you'll find that because delta V is less than 0, so your work, the amount of work done by the gas has to be less than 0. Okay, so just by looking at this two diagram, although you have the same initial point, you have the same final point, but the amount of work, one is positive, one is negative, and this tells us that heat and work are path dependent because it depends on the directions of the process. Different processes will result in different amount of energy transferred. Okay, so this quantity, heat and work are the quantities that are path dependent. It really depends on what kind of process involved, and the amount of heat or work involved will be different. In the next one, we're going to briefly talk about the first law of thermodynamics. And of course, we're going to discuss it more in detail in chapter 19. And this one just tells you, in this chapter, we just lay out the foundation and letting you know what the first law of thermodynamics is about. So the first law of thermodynamics tells us that the internal energy, okay, the internal energy of a system tends to increase if energy is added as heat, and tends to decrease if energy is lost as work done by the system. So all this basically you can write it in a mathematical form. This is a change in internal energy. So delta E is equal to Q minus W. So this Q, so this basically just when heat is added to the system, then the change in internal energy, of course, has to be increased because Q is positive. And then minus W, if the system does, some amount of work, then energy is lost because energy has to go into supporting energy has to be used in order to do work. So when the system is doing positive work, then the internal energy will decrease because it just lose that amount of energy to work. So delta E is equal to Q minus W, and in differential form, that will be D differential internal energy is equal to differential heat minus differential work. So the internal energy tends to increase if Q is absorbed. So in other words, heat is flowing into the system, then the internal energy is going to increase. And then of course, internal energy tends to decrease if the Q is being released by the system. Or internal energy is going to increase if positive work is done on the system. So this is positive work done on the system. In other words, you have a system and you have, let's say, the environment. If the environment is doing positive work on the system, which means that the system gains energy, as opposed to when the system does positive work. When the system does positive work, it does, the internal energy will be decreased because the energy goes to do the work, so it's losing its energy. The energy, the internal energy of the system will be lowered if it does positive work. However, the internal energy of the system will increase if positive work is done on the system. Okay, so the wording is kind of tricky. So you want to pay attention either the work done by the system or work done on the system. That'll be different. And there are several different processes that you're going to encounter when you're dealing with gas. Okay, one process is what we call the adiabatic. Whenever you read the keyword adiabatic, that means that there's no heat transfer. In other words, Q is positive whenever you have adiabatic. Okay, when you have an adiabatic process, Q is 0. So by applying first law of thermodynamics, if we look at this, when Q is equal to 0, what does that tell you? When Q is equal to 0, it means that the internal energy of the system would just be equal to negative W. So the internal energy of the system, the change of internal energy is equal to negative work done by the system. When you have a constant volume process, whenever you have a constant volume process, when volume doesn't change, it means that there's no work. When W is equal to 0, then let's look at the first law of thermodynamics. When W is 0, then internal energy has to be equal to the heat that's being transferred to the system. So if heat is transferred to the system, then internal energy is going to increase. If heat is released by the system, then internal energy is going to decrease. Okay. And then we have cyclical process. When you have cyclical process, because after cycle, that's an engine. After cycle, you go back to this original starting point. Whenever you're going to original starting point, nothing changes. Pressure doesn't change, volume doesn't change, temperature doesn't change. When temperature doesn't change, there's no change in internal energy. Because later in chapter 19, you'll find out internal energy only depends on temperature. So when internal energy is 0, it means that when you apply the first law of thermodynamics, it means that Q is equal to W. The amount of heat that's being added to the system is used to do work by the system, and such that there's no amount of energy is left to change the internal energy. So that's why internal energy is equal to 0. Okay, and there's another process is what we call free expansion. When you have a free expansion, because it happens so fast, and because it happens so fast, so it's almost so it is like it is a adiabatic process. When it is a adiabatic process, there's no Q, and also because it happens so fast, you can define the stage of the system. So when there's no when the state of the system cannot be defined, then you don't have a pressure defined, you don't have volume defined, so there's no work. So your Q and W is equal to 0. This is when you have a free expansion process. When you have free expansion process and QW is 0, when we apply first law of thermodynamics, you'll find that there's no change in thermal energy, and you'll find that the change in thermal energy is equal to 0. So one example for free expansion is Big Bang. When you have, at the start of the universe, when you have a Big Bang, so you have one starting from a point, and then you just undergo a free, because it's Big Bang, you go through the free expansion, and it happens so fast, and so there's no heat exchange with the environment, there's no work done, and there's no change in thermal energy. Okay. All right. So we talk about energy, we talk about heat flow, and we talk about work. So what are the mechanisms for heat transfers? In other words, when you have two objects, they are not in thermal equilibrium. How does heat transfer from one object to another? eventually they become thermal equilibriums. So what we know so far is that there are three different mechanisms, heat transfer mechanisms. One is conduction. When the objects are in contact with each other, then heat can transfer from one place to another when there's a temperature difference. And there's convection. Convection deals with fluids. When you have a fluid that's in contact with the object that has a higher temperature, then the fluid will become very unstable. When the fluid becomes very unstable, then you have convection or the turbulent motion, and then through that turbulent motion, then he can transfer. Just like when you boil your water, you have the pot and you have pot full of water, put it on the stove, you turn on the heat, and then you can start seeing that the water is flowing. With the time, with the increase in time and the increased temperature, the water gets hotter and hotter. When water gets hotter and hotter, you can see if you follow the motion of the water, you'll find that it's basically cause the turbulence. It's kind of like it's flowing. Let's see, is basically, let me see where I can draw. You can see that this is the stove, and this is the pot, and you have water, and then and the water just go from this to here, because hot water is lighter and cold water is heavier. And when you have when you are heating the water, then the cold water because it's heavier, so they will be on the bottom of the pot. But then when it gets heated, then it'll go like this, go up and then comes down, so it becomes the turbulent motion or convection. And that's how they, because the mixing, the cold water and the hot water mixed together, so that thermal equilibrium will be reached eventually. Okay. And so the third mechanism is thermal radiation. Heat can be transferred via via electromagnetic waves. And when we talk about electromagnetic waves, we know that it does not need a medium in order to for it to propagate. It can propagate through a vacuum. So no medium is needed for the heat transfer. Okay. Now let's look at the first mechanism, conduction. So let's say when we look at this picture, we have one hot reservoir which has a temperature maintained at T sub H, which has a higher temperature than this cold reservoir, which maintain a temperature T sub L. So you have two different objects, two reservoirs, and between them is sandwich. You have an object that's sandwiched between these two reservoirs, and because this temperature T sub H and the T sub L, they are at different temperature, so we know that heat is going to flow. It's going to flow from the hotter objects to the lower temperature objects. Okay. So the question is, what is the rate of transfer energy? So in other words, the power or the thermal conduction rate. So the thermal conduction rate is defined as the amount of heat transferred within the time t, and what we found is that it's equal to K, which is the thermal conductivity, times contact area A, and then times the temperature difference of these two reservoirs, and divided by L, which is the distance that the heat has to propagate from the hotter reservoir to the colder reservoir. So the thermal conduction rate is K times A times temperature difference over the distance that it has to travel. Okay. What about when you don't just have one material? You have like different materials. Let's say two materials, and you have this first material has the thermal conductivity K1. The second material has thermal conductivity K2, and then the first object has the distance or has the thickness of L1, and this one has a thickness of L2. But the contact area remains the same. They have the same area A. So in this case, thermal conduction rate is equal to the contact area times the temperature difference of the reservoirs divided by the summations of L over K. L, of course, is the thickness, and K is the thermal conductivity. So I should write, I say Li and then Ki. Okay, so depending on how many different objects sandwiched between these two reservoirs, and then you can decide how many turns there will be. If there are just one, there's just one. If there are two, then there will be 2 turns. 3, then there will be three turns. So we also define the quantity, which is we call a thermal resistance. This is like, so we use R. This is not electrical resistance. This is thermal resistance, and that's equal to the thickness L divided by the thermal conductivity K. Okay, so different object will have a different thermal conductivity, and so so let's say in this case, let's say you have K1 and K2, and they may have a different thickness L1 and L2, and then you can calculate what would be the thermal conduction rate, and so that's that. Now the one last slide is the third heat transfer mechanism, which is the thermal radiation. Okay, so for thermal radiation, let's say you have an object, and this object radiates certain amount of energy, and how much energy is radiated by that object per second. In other words, what is the thermal radiation rate? So the thermal radiation rate that is radiated by the object is equal to a constant. This constant is what we call the Stefan-Boltzmann constant times the epsilon emissivity of the object surface times the area of the object, and then times the temperature of the object to the fourth power. Okay, so in other words, let's say take for example, a human body. So you have a Stefan Boltzmann constant, which this quantity of course can be you can check out its value in the book, and then you have the emissivity of the object surface. Okay, so different object will have a different different m. So let's say for human body, you can take it to be 1, or it can be 0.1. Depending on the object, and then the surface area of the object, so your surface area, and then times the body temperature to the fourth. Okay, and then so this is the amount of energy that is being radiated by you per second, and the amount of energy that you as a human body absorbed from the environment is equal to Stefan Boltzmann constant times the emissivity of the object's surface times the surface of your body, and then times the temperature of the environment to the fourth. Okay, so this one is the thermal radiation rate that is being radiated by you, and this is the this is the rate at which your body absorbs the radiation from the environment. So the net rate of energy exchange will be the amount of energy absorbed by you per second minus the amount of energy radiated by you per second, and that's equal to the constant times epsilon times the surface area times this quantity. Okay, within the parentheses. So we pretty much finished chapter 18, and so that's it.